So, okay, maybe I move this a little bit more out of the way here. So, as I said, the idea for this next bit of a lecture is that we talk about what we've been doing in the Trishuli with building our own stations. So no Python programming now. We'll get back into that a little bit later and more tomorrow. So some of these logos you probably recognize from R or from Python like we used this morning. This is from Raspberry Pi and Arduino. In the last years, there's been just a huge number of these open source hardware projects. So not just open source software, but open source hardware. So the designs are all publicly released and anyone can work on these kinds of machines. So this means that when we have this open hardware and this open software and we put them together, we can do things much more low cost than you can if you go to a company and say, I want to buy this fancy monitoring station. They will often do some charges for their proprietary software and all these kinds of things. So when we're working here in the Trishuli, we're generally working with open source software and open source hardware. So we base most of our sensors that we're building around two different platforms. One, you might recognize, this is Raspberry Pi. This is basically a small computer. You can plug in a mouse and plug in a monitor and use it just like you use your laptop. It's a little bit slower since it's only the size of my hand or so, it's quite small. But for something like collecting camera images or collecting the GNSS data that Bodo was showing, this is totally fine. You're just reading in some data. On the other hand, this is one example of an Arduino sensor. This is also an open source hardware, but you can't plug in a monitor. It's not for using like a regular computer. What it does is it translates data from any kind of sensor, an air temperature sensor, or Shakil is doing some stuff with air quality monitoring. And so they have these sensors that you need to translate the data from the sensor to something that your computer can read. So you can plug it in on a USB and just read the data. So that's what this side is doing. You can sort of split it into this collecting data, storing the data, and sending the data. So when we have data way up in the mountains, it's nicer to not have to go there and collect the data. So we usually use a SIM card or something like this. And the Raspberry Pi is also involved in sending the data. And on the other hand, when we want to connect to these sensors, we use the Arduino. So, for example, to look more specifically at what some of these sensors look like, Arduino was started as sort of an open source project. Let's teach people how to do real electrical engineering with these little microchips. Work with the raw data. You get some numbers and you have to translate them into something you can really understand. So they wanted to make this low cost as they can, and they wanted to make it open source so that it could be used for education and in places where the budgets are sometimes lower. So like I said, you can't use them like a computer, but you can use them to interface with all sorts of different hardware. So this is one example of a sensor that we've been using up in the Trishuli, and the Arduino board is this part here that's translating the data from an air temperature sensor and the LiDAR. And these LiDAR, they're just coming out as these wires, right? It's not like a USB that you can plug into your computer and it tells you what it's saying. You have to have some piece in the middle that translates the data and sends you the part that you want. So that's what this Arduino is doing. Each of these boards is really only for one task. You give it some simple code and it says, every 1 second, check what the temperature is, and then send it to me. So it has one exact task to interface with these sort of very low-level sensors and send you the data. The nice thing about this is that since this is all published open source, lots and lots and lots of people have made sensors that work with this platform. And they've tried to also keep them rather on the lower cost side. And the power consumption is also quite low. So something like this you can run off of a battery for several months. So if you have somewhere where you don't have power, but you want to put a camera and it takes one image every day, this kind of sensor can run on a battery and wake up once a day, take a picture, go back to sleep and save power. So it's very flexible for all sorts of different kinds of sensors that you want to build. So, for example, when you buy or you want to build let's say a weather station, right? If you want to go on campus or you have a research field site and you want to know the temperature, the rainfall, humidity, all of these things, you can go to a company and get these automatic weather stations, right, that are installed all over the place. And I just looked one up the other day and it was something like 8,000 euros, right? This is quite a budget for something that has temperature and rainfall. It's doing 4 or 5 different things. But it's quite expensive, right? And if I look at the actual little microchip that they're using to measure the air temperature, it could be something like 5 euros, right? So this is a temperature and humidity sensor. It doesn't have this whole interface. This is what we need the Arduino for. But we can get the exact same data that we get from our fancy automatic weather station for more like 20 euros. So quite a big difference from 7 to 10,000 euros, right? It means you have to go in there and construct it yourself. You have to have a little bit more knowledge about which pieces to put together. But if you have a lower budget, or if you want to spend 10,000 euros on making 20 stations instead of just one, then this can be a good strategy. And like I said, since this is an open platform and there's so many different use cases, these microchips are extremely flexible. Anything that you want to try to measure, you can probably find the sensor that will do it. Some of the temperature sensors that we're using for the water were designed for like these food transportation trucks. So they put them in the truck and make sure that it was always cold enough, and they're not going to give people food poisoning because the fish got too warm, these kinds of things, right? So some company needs 10,000 of these to put in their trucks. So the cost is quite low. They're mass producing these sensors. So there's all these different places you can find sensors for anything you want to measure, and they duplicate a lot of these functions from these fancier sensors. You just have to put it together. It doesn't come pre-packaged for you. So into a little bit more specifics of what we've been doing and where we've been doing it. We have several different stations, some of which Bodo showed earlier. This was our lowest elevation station, this one that's about 500 meters. And then the second one that Bodo was showing about 1,700 meters is up here at this guest house, and we have even one above. So I think now we have, what, 10 sensors or so that are in there. And this is where we are in Kathmandu, and they're all up the Trishuli watershed. The goal of what we wanted to do, the things that we really wanted to measure were river temperature, river height, so stage, water vapor, like Bodo has been showing this morning, and then pictures of the river. And so by putting these things together, we get an idea of all sorts of different changes in the water. When the temperature changes a lot, there's either some rainfall coming in or a shift from snowmelt to more groundwater contribution. This can tell us a little bit about the hydrology of these parts of the river. The height, I think everyone can understand why you might want to monitor the river height, see how fast it can change after a rainstorm, and check for flooding and these kinds of things. And then the images we will keep working on a little bit more this afternoon. But I think they're quite interesting for capturing sort of these short-term changes in the river that you can actually look at, right? It's not just lines on a chart, but really showing you what's happening. And one of our main goals was that we wanted to make all of this open source so that anyone could follow our plans here and make similar instruments or use this same idea but install different kinds of sensors. So just to give you some examples of how we are measuring it, what these things really look like. So to measure river temperature, which is really useful for knowing dissolved oxygen, water quality, or what's the snowmelt input. You can also have an idea of when different inputs are starting to mix and when the temperature is changing. And this we were doing with a thermal camera, which cost maybe 40 euros to put together. It's sort of half and half between the Arduino and this little tiny thermal camera. For river heights, we were using LiDAR. Some of you have maybe heard of LiDAR. It's like a light detection and ranging. You basically shoot a beam of light or a laser at a surface, and it measures how long it takes to come back. So if you have a nice platform like a bridge that's on top of the water and you point it straight down, it can measure every second how high your water is. So you can get a really fast idea of, is it changing every 10 minutes? Does the water come up really fast during some floods and not other ones? This is the kind of data that we wanted to get at. And this one you can get, this one's a little bit more expensive, maybe around 140 euros, but still not towards our 10,000 euro weather station. For river heights, we also used GPS data. So this same data that Bodo was looking at this morning, talking about water vapor, you can use a similar strategy to understand how high above the water your GPS antenna is sitting. So if you think about these, everywhere in the world you're getting these GPS signals getting shot down at the earth, right? That's how our phones know where we are. And if some of them come straight to our antenna, and some of them come and hit the water and then reflect to our antenna, the difference in this time can tell us from some trigonometry how high this reflector is, how high is our station above the water. So through time, if that distance is changing, you can say that the water height is also changing. And for this, you don't need a slightly fancier GPS that Bodo is using for the water vapor. You can use something that's more like 30 euros. And this can give you water height every 15 minutes. So it's a quite a nice low-cost way to measure these big flat water bodies. It's a little bit trickier in steep valleys, since you are always blocked on some sides by the mountains. But if you're down more in the floodplain, and you have a wider river, this can work really, really well. At our lower stations, this works really well. Way up at the top, where it's like a really steep gorge, it's a little bit trickier. I guess this is the same slide that Bodo was showing also about this water vapor. I don't need to talk about this too much, but this also gives us another idea of not just what's coming out on the river, but also what's going up, right? How is the water vapor going up the valley, and how is it coming back down in the rivers? So that's why we wanted to collect water vapor as well. And finally, we wanted to capture images. So for this, we used this Raspberry Pi camera, since this interfaces directly with our Raspberry Pi that we're using to collect and store and transmit our data. But you could use a USB camera or even a webcam. Something like this would also work totally fine. When we were talking with some of the hydropower guys, they have a webcam that's pointing at parts of their intakes, so they know every second they're watching it on a camera, is the water going higher or lower. You can use the same principle with some webcam and capture images. We just use this one because it's quite affordable, like 20 euros, and we can capture exactly the kind of data that we want. The main constraint on where you want to put this kind of sensor is power. Can you power it over some time? Is there access to electricity? Can you put it somewhere where it's secure? Is it somewhere where somebody's not going to come and take one piece off, or if you have a solar panel, maybe they want to borrow it to use at their house, these kinds of things. So somewhere that it's secure. And if you want to be able to check on it or get the data without going there, then you need either some Wi-Fi access or somewhere where there's a cell phone network. So we've had quite some difficulties at some of our stations getting the data remotely because the cell towers are not so powerful up there in those steep valleys. So that can also be a constraint. If you want to capture a lot of data and it's hard to send it back, you have to take this into account. So this is an example of one place that we installed a sensor. So it's up on one of these berms on the side of the river, and the sensors are looking down at the water. So they're capturing how far away the water is from our sensor, how warm it is, taking some pictures so we can see, for example, the color of the water, or is it coming higher or lower? This kind of data that we can then translate into what's happening in the river. This is another example up a little bit higher, which I've labeled a little bit better. So those little sensors that I showed you, right, that's just a microchip and a little thing hanging off of it, we put them in these little boxes. So you want to go into some sort of weatherproof box as well as you can. In the monsoon, weatherproofing can be kind of tough, but you want to keep things as dry as you can. So we use these sealed boxes, and then we have, for example, our thermal camera and our camera and a LiDAR and a GPS. So all of these things are then transmitting data together. So we're storing all the data. And this is just the same sensor from a side view. So this is where we're looking down at the river. The other kind of stations, the ones from the GNSS data that we're using for water vapor, the ones that Bodo was showing you the data from before, they can be a little bit further away from the river. You don't have to be so directly at the river to understand what's happening with the water vapor. So those ones we prefer to set up more on, for example, roofs or really high structures that were out of the way, and we could put them more on a permanent installation. So for example, this one is up on the top of a electricity board building that they gave us some access to, and they just ran a power cable up from one of their storage sheds, and it just sits there now. And we put some cement down and bolted it into the roof, and it should stay there and not move. And it just collects the data. In here we have then a battery, so there's a little bit of a power backup if the power goes off for some hours, and then the Raspberry Pi that sends the data back to us. This would be another sort of example. This is on some hydropower infrastructure by one of their intakes here. And you see again, we have the sort of transmission box. This is where the data is all collected and where the power is coming in. And then the different sensors all pointing down at the water. So yeah, this is the main thing. You've got to find a place that you can securely put your sensors and have power. And after that, you worry about the data transmission. So back to how we're actually doing this, taking all the data from these sensors, we're using the Raspberry Pi, which we can use, basically we can run all the sensors onto USB cables. All of these Arduinos can send the data on USB. And so we plug them in, and then we write some Python code that's running all the time in the background. And that checks, what is this USB sending me? Is it sending me data? Okay, let's store it to some files, and then we send those files onwards. So this can take in 4 or 5 different USBs, so you can have 4 or 5 different sensors, as well as something to have the SIM card and send the data. So what does this data actually look like? So with these kind of sensors, when you design it yourself, you can collect data really, really fast or much slower, depending on what you want to study. So when you design your own sensor, you can collect every 1 second if you really want to. So for example, we have this really high frequency temperature data from our few different stations, and the temperature gets higher the lower you go downstream. It's warmer when this water has been going down further, and it's being warmed more by the sun. So we get a really, really detailed view of the fluctuations in temperature over very short timescales. If we compare that to what we would get from, for example, Landsat, where we can also measure water temperature over specific parts of the river, this is our whole coverage period for almost 10 years. And this is the same coverage period as this, I think. So this is from, so this is from May until November, and this is from June until November. So we're comparing this to this. This is why you really sometimes need this in-situ data as context. If you show me this, I'm not going to know anything about what's really happening throughout the day or even throughout the year with this water temperature. But this can give me much more detailed information. On the other hand, if I want to go 500 meters upstream from my sensor, then I have to look at Landsat, right? I have no idea the parts of the river that I can't see. The river heights, we also get quite detailed information. For example, this is from the GPS data. So every 15 minutes or so, we can see throughout 1 year or 6 months that we have basically a 3.5 meter change in the water height at this station. So it's going from 11 meters away from the station, so only about 7 meters away from the station. You can see there's quite some noise in there, but with some filtering you can bring this down a little bit more. The LiDAR data also gives us a very, very detailed, much faster view, but for this you need a really good sight that's looking right down at the water. And then finally, I think the most fun one and maybe the most intuitive one to work with is this camera data. So if you have a camera that's fixed, you can take images all throughout the day, you can take it every day, and you can see, maybe I go back and forth here, that at the beginning the water level is quite low, right? And then through the monsoon it's coming up and up and up. And if you look at these images, you can measure, for example, where is the bank and where is this bank? And you get how full it is. If you have some idea of how wide the river is, you know a little bit more about the discharge, or at least the channel width throughout the year and how that's related to when the rainstorms are coming. So just to go from the first image to the last image, you can see that things have changed a lot, right? We're from a much smaller river to a much, much bigger river. From this we can get, like I said, these like bank width changes, for example. We can also look at the color. It's quite different, right? This is a little bit clearer and this is a little bit muddier. So you can say something about how much sediment is being carried at different times of the year. If you also take some short videos, so when you have a camera, you don't have to just take images, right? You can also take videos. And when you have videos, then you can try to get an idea of the flow and velocity. So how fast is the water actually moving? If you have flow velocity, an idea of the amount of water from how much this bank has changed, you can turn that into discharge. And that's exactly what they want to know for hydropower or for flooding and these kinds of things. Discharge is the real thing you want to know for hydrology. So here is one, oops, let's see, can I get this to play? Yeah, so here's one video. I think it's only 30 seconds, right? And we can see that the water is moving, and you can see if you have some little white patches, some bubbles, and you see how they're moving, the computer can find these little patches and track how they're moving. And from that, you can get the speed of the river. So you just need a 10-second video or a 30-second video, and you can get the flow velocity. If you do this once an hour or once a day, you can measure the flow speed also throughout the year, just from having a camera. So I think the camera data is quite cool and very flexible for a lot of different applications. Of course, we're focusing here on rivers, but you could use the same thing to point at a stand of trees, right? And see when they're green, when they're losing their leaves on a very detailed level, right? Or point it at a glacier and see when it's moving faster or slower, or when there's snow and when there's not snow. It's quite flexible, the different kinds of things you can do with it. So again, I put then this whole PDF online, so you can go and see all these links. Also, if you're more curious about these sensors and how to actually build them yourself, or send one of us an email. We're very happy to discuss these things if you have specific things you want to measure. Shakil sends me emails quite often asking about these air quality sensors that they're building there in Finland. The Arduino and Raspberry Pi teams also have quite detailed manuals and courses. So you can go through these and figure out exactly how to measure what you want to measure. And I think that's it for my intro.